Stars, I'm a fool for your love.
Hello everyone, it's Chris Bachman here again from Cal State LA, putting together a short video on some of the key aspects of suspension design. Let's get right into it. So, talking high level, what are some of the objectives of the suspension subsystem? As we saw in the overall vehicle short, maximizing grip has a big effect on your lap times. And so maximizing grip involves your tire selection, the positions of your tires, the angles in order to maximize grip, and to minimize any variation in the normal force. And that comes from what we've talked about several times now. Over on the right, one, this is different inclination angles. You can have different grip based on your inclination angles. Here we're saying that this tire straight up and down gives us the most grip. And you might also see that typically as you increase the downforce, so this is going from 50 all the way up to 250, that you actually decrease your available grip as you increase the downforce, at least on a per downforce basis. And so you want to minimize the load transfer from tire to tire and the load variation. So another thing you might want to do, especially in the case of Baja, where you have quite big obstacles, you might want to reduce the sprung mass acceleration and the accelerations felt by your driver. So here's an example of some 3-foot whoops in this little quarter car suspension model. You can check out some of our workshop videos if you want to see how to make these. And so what I'm plotting is not only the position, but also the forces, right? And so in this case, you might want to reduce the forces felt at the sprung mass, which will be transitioned to your driver. So keep that in mind. And the last thing is, especially provide ride height for the sprung mass. You need to design your suspension so that you can overcome all of the obstacles on the course. Last, just like any subsystem, it needs to really support your overall vehicle objectives. And so there'll be compromises to be made with your suspension in order to optimize the overall performance of your vehicle. One example, you hear about a little bit this year is Mercedes compromising some of their rear suspension in order to optimize the aero in that area. So so keep that in mind. And as I'm also sure I'm forgetting some things here. It's kind of a catch-all. So let's go a little bit into tires and rims, right? So hopefully you've seen the tire test consortium data for formula for Baja. Hopefully you're looking up some data, and you want to maximize the grip. So forces in the lateral and longitudinal direction. You might also think about things like restoring moments and using that as in your trade study to help you select your tires. So one other thing to think about with the grip is you'll usually have similar ratios between the grip on the front and the rear axle, and you might use the maximum grip values or corner inch thickness or tread width, and that ratio is usually on the order of the weight distribution of your vehicle, your aerodynamic downforce, as well as your roll stiffness distribution. These are usually close to each other, and that'll help you be able to tune in and adjust the performance. I show a couple tire testing rigs here for on-road and some off-road rigs as well. You might also want to think about the mass and the rotational inertia. You might have really big tires that have great grip, but they might have high mass and high rotational inertia that you need to carry around with you, which will you might end up being slower overall. You might also think about temperature, especially in the case of formula. Their tires, you're not allowed warming blankets, so you're going to be going into a lot of events cold initially. How long does it take the tires to heat up? How do they perform while they're cold, right? Another thing you have to keep in mind is if you want to go to light or small tires, you might run into packaging issues. You need to get your uprights and brakes typically inside these inside your rims, and so there'll be some trade-offs between your ability to package your suspension system and your choice of tire and rim selection. Last but not least, vehicles are very dynamic, but we look at a lot of things using steady state analysis because it makes it more tractable. But vehicles very dynamic, and so you might consider some of the dynamic behaviors of the tire, not just how long it takes to warm up, but things like relaxation lengths and that sort of thing. So we're just getting into looking at this. So if you got a lot of info here, feel free to reach out to us. We'd love to learn more. So those are kind of some of the key trade-offs you're thinking about with selections of your tires and rims. So you might also think about, well, where should we put these tires on the ground? What should we have our wheelbase, which is the distance from the center of the front tires to the center of the rear tires, or our track width. So kind of just rough trade-offs in terms of increasing the wheelbase. You find you'll have increased stability, especially at high speeds. You'll have decreased longitudinal load transfer. You're going to have more room for packaging. On the downside, it's going to increase your turning radius, which will reduce some of your agility, and it'll increase your moment of inertia typically. So what typically seen in this case is the reasons to decrease the wheelbase usually outweigh the reasons to increase, and so usually the wheelbase is getting pushed as small as possible to package the driver and the engine and the drivetrain, or to small as possible, meeting the rules in the formula case with the 60-inch wheelbase rule. And that way you can increase your agility and decrease your moment of inertia. Track width, the one thing that happens when you increase your track width, and we'll talk a little bit more here, but you've also seen that in some of our earlier videos. If you've seen them, is you'll have decreased lateral load transfer, which is ideal. But again, you're going to have an increased turning radius and increased moment of inertia, and so it might have some downsides for going too large. So the track width is not as easy of a discussion because you don't necessarily want to maximize it or minimize it, and it's a little bit harder thing to simulate. But some other downsides considered, like in slalom, the larger your track width is, the more you actually have to veer from left to right to go through the slalom. But just to give you some rough kind of rules of thumb to get you going, is that for example, like go-karts, where you have these very slow, very windy tracks, will usually have roughly track width equal to the wheelbase. And you go to higher speed race cars, your track width might get to about 60% of the wheelbase, and then you might have cars that don't do a lot of turning and are just straight line like dragsters, and your track width might be about 20%. So in the case of Baja and Formula, I'm probably in the range between kind of the go-karts and high-speed race cars. And so, Baja is even a little bit lower speed, so you might see them get closer to 1-to-1. You need to keep in mind this is just rough orders, rough rules of thumb. And Formula might be you might have a little bit smaller track widths that are on the range of 80% of the wheelbase. So the next thing I want to talk about are all the different angles that your tires can make with the ground, as well as the position and angles of your tire relative to the steering axis, so the axis about which the tire will turn when you're steering the steering wheel. Next, let's talk a little bit about the toe of your wheels. So this is looking down from a kind of bird's eye top view of your vehicle, and this vehicle is going forward. And so in this case, when the tires point in at the front of the tire, and so they're closer together at the front, we call that toe in. And when the wheels are pointed out, we call that toe out. So usually toe in is considered more stable. So it's pretty common for the front wheels to be at the forward part of the wheel to be about 1/8 of an inch closer than at the back side of the front tires. And then toe out is usually considered less stable, but said to be a little bit more agile in turns. And the rear tires are usually closer to neutral. So the next angle to talk about, which will have a big effect on your performance, is camber, or also known as the inclination angle. It just uses a different definition of positive and negative. So camber is more common. So this is kind of thinking of a rear view, looking at a left tire, showing kind of the upper control arm and the lower control arm. So it's the UCA, LCA. So if the tire at the top is away from the vehicle, we call that positive camber. And if the tire is at the top is towards the vehicle, we call that negative camber, and zero camber straight up and down. And you'll see the inclination, the definition of positive and negative inclination angles, and those are just important for single tire tests where you don't have a center of vehicle to reference. So typically tires want to be close to vertical in order to maximize grip, or have a little bit of negative camber. And what you want to make sure to do is keep your tires from going into positive camber while you're going into turns, and keep in mind not only because of roll and the tires traveling in roll, but also just compliance in the system can cause your tires to go into positive camber, where you can lose quite a bit of grip. So let's start to also look at the tire compared to the axis of which it's steered about. So here I'm showing, again, a rear view of potentially a right tire, and you have what I'll call the upper ball joint and the lower ball joint. And if you draw a line between those two, that's your, we'll call the steering axis. So when you turn your tire is going to turn about that axis. And if I draw a vertical line in red here, so this is supposed to be perfectly vertical, the angle between that vertical and the blue line is the kingpin inclination. So additional kingpin inclination will help with some straight line stability, because as your tire is turned, it'll actually dig down into the ground. And so the most stable position for it will be to be going straight forward. But too much kingpin inclination and your tire will go into high camber angles when your wheel is turned. So it's a compromise there. And if you draw a line, if you extend the steering axis to the ground and between the center of your tire, center of your contact patch really, is your scrub radius. So the larger this scrub radius is, the more feedback you'll have to the driver, because the forces happen at the contact patch. And so that'll create a moment about the steering axis, which is held by your tie rod of your steering system. So that'll give your driver more feel, especially in this view, the braking forces will cause moments. And so, but too much and the braking loads will increase in your tie rod and your steering system, which are holding these. And so you might think about having that in tension instead of compression, so that it doesn't buckle under compression. Next, I'll talk a little bit about the caster angle and trail. So here I'm looking at a side view of the tire. Again, I'm showing the upper ball joint and the lower ball joint, and the direction of motion being forward. And so this is, again, the steering axis in blue. And when you extend it down to the ground, if it's in front of the vertical line of the contact patch, we call that trail. And then this would also be a positive caster angle. You can have a negative caster angle and a negative trail. And you can also have a negative caster angle and positive trail. So that's like a shopping cart scenario. So typically you'll want to have some positive caster, because the inside, so imagine we're going in a turn. I'm picturing the inside wheel, so a right-hand turn, we'll say like the front right wheel. As you turn to the right, the tire is going to, that inside tire is going to dig and go down into the ground, whereas your outside tire is going to lift up. So it's a little bit different than the kingpin inclination, where it'll go down into the ground in both directions. And what that helps do is, because your inside wheel in the turn was going down into the ground, it's going to actually help, provide some load transfer from your outside wheels to your inside wheels, as you're effectively rolling your vehicle into the turn with this caster. And that'll help counteract some of the weight transfer that's inherent in a turn, which hurts your overall traction. So the trail in this case is also very important, because it provides stability. So you imagine if whenever you all of a sudden started pulling your shopping cart backwards, the wheel would kind of jam before it flips around. And so your contact patch wants to trail behind this steering axis so that it's stable. Similar phenomena to not having your centers of pressures and arrow in front of your CG. And so you usually want some positive values for both. All right, so I've just finished talking about some of the static angles and geometry that are important for your tire with the ground and the steering axis. But we also need to think about your tires needing to be able to move. So there's quite a few different suspension types that are out there that are worth looking at. But in all, the upright of your suspension will have 6 degrees of freedom that you'll need to restrict. And so one of the more common ways to do this while providing independent motion of each wheel, because you don't want, for example, in this tube axles, which you've maybe seen on the back of a truck or old car, if one wheel gets upset or gets some motion, it's going to affect the other one. So the most common is, especially for formula vehicles and the front of a lot of Baja vehicles, you see these unequal length converging wishbones, or they call them A-arms. And in the case in Baja, you will see more novel wheel suspensions with some swing axles or swing arms in those cases. So, but I would start out by you want to learn a little bit more about these and getting better pictures of these different suspension types. This book by Costin and Phipps is great to see the different ways which you can fully restrict the 6 degrees of freedom, with the last typically being controlled by your springs and damper systems, because you do want the wheel to travel, but in a controlled manner. So one other thing I want to mention is that while each wheel can move independently, typically that's not the modes in which we look at the vehicle. So the 4 that we usually break it up into is roll. So this will happen when you have lateral acceleration. Your vehicle will roll, and here we're showing the tires moving relative to the vehicle. But of course, in the roll situation, typically the tires are actually all on the ground, but it's actually the center of the car that's rolling. But this is another way to look at it. And so you also have pitch, and so this happens when you're braking or when you're accelerating forward. Your vehicle kind of dive forward or squat back. You have the heave mode, up and down, so the whole vehicle going up or down. This is pretty common in the case of aero, where you will have a lot of downforce. And then you have the last mode would be warp, so the rear axle relative to the front axle, and that's the ones we usually decouple. You potentially think about and decouple them into. And more advanced suspensions can actually even control. We'll have different characteristics for the stiffness and damping in these different modes. But I'll talk a little bit more about kind of a simpler design, where we focus a lot on the kind of heave motion up and down of the front versus rear axle, as well as looking at the roll, as well as looking at the roll characteristics. Next, I want to talk a little bit about just a simple case of roll and keeping your tire vertical with the ground through roll, as we've seen that we would not want our tire to go through positive camber. So here I've drawn a vehicle, and this vehicle is rolled like we're doing a right-hand turn. And I've drawn the tire where it would normally be under the static case, and it's actually had to move up as the vehicle rolls by the roll angle times the track width divided by 2, which is just kind of it's just a arc is equal to the angle times the radius. And if we want to look at how much has the tire had to camber to stay vertical, that's also going to be equal to the roll angle. And so, for example, kind of what dynamic camber that you'd want in this case, you'd have the camber gain in this scenario divided by the wheel travel, and you see that really depends on your track width, how much camber gain you would need to have through travel in order to keep your tires vertical. And so I just threw in a typical value, but you might want a few degrees per inch of travel in order to keep your tires vertical in the roll scenarios. So let's talk a little bit about what will control the amount of roll. So I'm looking at a simple swing axle case. So in this case, we have our suspension is connected at a point here, and it goes and it holds our upright, and so our tire can swing up and down, and you can think about it swinging about this point. And so CP stands for contact patch. So this point can swing about this arm here. And so because it's swinging about this point, we call this point the instant center. And so if you think about these wheels being stationary and this having your center part of your vehicle, which we'll call the sprung part of your vehicle because it's typically sitting on springs, it would have to move, if these points were fixed, tangentially to this instant center here and here. So when this actually rolls without moving the tires, you'd extend these lines tangential again here, and you'd get to your roll center, which would be right here. So this is where the vehicle rolls about. And so when designing the roll center, we usually think about the height of the roll center. It can move around laterally, and so that's one thing to keep in mind as your wheels travel. But first, let's think about it in the static case. So the higher this roll center is, if it gets all the way up to the center of gravity, the difference between the roll center and the CG would be 0. And that difference we call the roll moment, because the mass times acceleration term times the moment arm to the roll center is what's going to cause it to roll. So if you get this all the way up at the CG, you're not going to have your vehicle's not going to roll at all, which could be good if you are unable to do what I talked about on the previous slide, which control the camber of your wheel through travel. But most likely you'll be able to design it so that you can control the wheel angle with the grounds through travel. And there's a downside to that, and one that all of your weight transfer happens not through your suspension, but through your springs in your suspension, but through your suspension links, which happen very quickly. So you'll have the dynamics of your lateral load transfer will happen very fast. And in addition, because this acts kind of like a two-force member, so forces on the contact patch act along this line here of this two-force member. When it's very high, it'll also push on the sprung part and raise it up, and we call that jacking. So in case of like the VWs with the straight swing axle actually had this problem a lot. And so what we'll typically do is actually put the roll center closer to the ground to minimize the jacking and accept some of the roll, but controlling the tires so that they maintain adequate angles with the ground throughout their travel, which can be easier said than done. A couple other things to keep in mind is that the roll center should travel, typically you're going to want to travel with the CG in the heave modes so that your roll moment isn't changing, as that would feel awkward for the stability of the driver. There's already so many things changing dynamically through the turn that you want to minimize the number of things that are changing. In addition, as the motion of the suspension travels up and down, you don't want necessarily the tires to decrease in track width, as that would cause them to scrub across the ground, which could hurt your traction. So, but most of us aren't running swing axles. So how do you find this instant center and roll center in these cases? So what you'll typically do in these cases is you'll extend your upper control arm and your lower control arm out in space and get a point, and that's your instant center. So you can think of your tire moving about that. And then to get your roll center, again, you just draw a line between this contact patch and that point, and where it intersects with the other tire, same with the center line in the static case, or in all cases where it intersects with the same thing you do on the other tire, that would give you the point at which you roll about. And so keep in mind this was kind of in the rear view. The same concept gets applied to the side view of the vehicle for the cases of rather than roll, but in pitching. And so typically you'll again extend these lines to get kind of a front and rear instant center. And typically you'll talk about these more decoupled with the front and the rear. I'm not actually exactly sure why that is, so we'd love to learn more. I think it's mostly because when you're diving, most of your force is on your front tire, and when you're squatting, most of your forces are coming from your rear tire. But they'll typically, they won't talk as much about it as a pitching center, but they'll talk about how much anti-dive you have. And so because you extend this line from your contact patch to your instant center of your front wheels, and when it crosses your CG, it's at your CG, you're said to be 100% anti-dive. So when you're braking hard, your nose isn't going to dive down. And when you're accelerating hard, you have the same thing in the rear. So you have 100% anti-squat. And you also hear terms like side view, swing arm, length to help describe some of this motion in this view. And keep in mind that this pitching can be very important, especially in aero cases, because most of your wings and diffuser act in ground effect. And so if you allow your vehicle to pitch quite a bit, you'll want to understand the effects of aero in those cases, because it could upset the balance of your vehicle. Keep in mind that you don't necessarily want to have 100% anti-dive or anti-squat in the same way. You don't necessarily want to put your roll center right at your CG, because in that case, you're not going to have any motion of your suspension, and your car is going to be very stiff, and it's going to force all the higher forces into your tires, acting as your suspension members, which can upset your grip as well. So typically you want this to be as soft as possible, while not compromising other aspects of your vehicle. So at this point, I want to talk a little bit about designing the stiffnesses of the front and rear of your vehicles through looking at both a quarter car model and a half vehicle model in roll. And so this is looking at a quarter car on the front. Typically we'll break it up into a sprung mass and unsprung mass. The displacement between the sprung mass and the unsprung mass usually has a stiffness term, so we call that the wheel rate. So this is the forces on, if you put a force on the wheel, how much does the center of the wheel move? And you have wheel damping. And between the unsprung mass, which includes your tire, your rims, your uprights, your braking components, about half your suspension components. And the ground, you have your tire stiffness. So this is something you can get from tire data for if you apply a force on your tire, how much it deflect. So you can track, and you might have forces on your unsprung mass, forces on your sprung mass, especially from aero, and you can track the motion of these. And so and typically what we do is look at this for a quarter of your car. So like one of the front quarters of your car, or one of the rear quarters of your car. And what you'll typically find is you want to minimize your unsprung mass, because it's hard to control, because you don't have much control over your tire stiffness, and it's just also more mass to control in the system. So that's one kind of key thing that's important, not only just to reduce mass, but reducing the unsprung mass. So, and what you'll typically do is to find ride frequency. So this is the frequency at which the undamped sprung mass will vibrate against the ground on. So here you have both the wheel rate and the tire in series. So that's the reason for the funky K terms, along with the sprung mass and a conversion to Hertz. So for Baja, usually this is in the range of 1 to 2 Hertz. And in formula, it's usually in the range of maybe 2 to 5 hertz. The stiffer cases are for systems with more aero, as you want to control your ride height through different amounts of downforce. And typically you'll want to start softer to help with your grip, and then increase stiffness as needed to limit suspension travel. And so this will, if you know your sprung mass in the front and the rear, this can help get you the wheel and the tire stiffness, which you can get from data. This will help you get what the wheel rate you want in the front and the rear. And typically you'll have the ride frequency of the front will typically be on the order of 10 to 20% lower than the rear, partially because you don't want some resonance between the front and the rear, but also because of the getting the front to be gets upset first when going over bump, and then the rear, and then having them return back at the same moment, so that your vehicle is returned back kind of at static conditions as quickly as possible. So you might pick something on the order of 1 hertz for the front for like a Baja vehicle, and 1.1 to 1.2 hertz to start. And if it's too, and again, I would start soft and then go stiffer as you need, based on not running out of ride height and for obstacles, and not running out of ride height in roll. And you can also use some of this relationship and what's known as the damping ratio. This is this funky zeta term, and the CW is the damping ratio for the wheel. And typically this value can be different for whether you're in compression or you're in rebound. Rebound, you usually want it to be quite a bit higher, maybe two to three times what you have in compression. You might also have it different for high speeds or low speeds. So keep in mind, none of this don't necessarily need these to be linear, but typically for dynamic systems, you want the damping ratio to be less than 1, which means it's under damped, usually in the 0.7 range, so you get good control but fast dynamics. But you can confirm this with tuning and more detailed models, but just to get you in the ballpark of what some of these numbers you'd be looking for are. Next, one thing to keep in mind is that we were talking about how much your wheel travels, but what you're picking for your shocks and dampers might not necessarily be the same as those wheel rates. And that's because your shock doesn't necessarily move the same amount as your wheel. So we define something called the motion ratio, which is the ratio of how much your wheel travels, how much your springs travel. And sometimes you'll see the inverse of this, also known as the installation ratio. So it can be kind of confusing. So just make sure which one you're talking about. In this motion ratio, you can imagine that the further your shock is mounted closer to the wheel, the more it will travel with the wheel. If it moves all the way back here on I'm showing it mounted on your lower control arm, it's going to move less. And the more vertical it is, the more it will move as well. If this comes down all the way flat, then it's going to move less than it would if it was vertical. And so understanding how these terms affect your motion ratio is important. There's actually, if you get more into the exact analysis, there's a term involving instance center, which you can include, but I'd recommend just building your CAD model and seeing what the motion ratio would be in that case, because you might even have rockers and push rods and pull rods, and using that and comparing that to what you'd actually measure on the vehicle. But just keep in mind that we've been talking about wheel rates, and what you actually need for your shocks might be different based on the ratio at which they travel. So we've looked a little bit about, all right, let's get get in some first numbers for what some of our stiffnesses and damping should be from the quarter car model. Next, we can look at the roll stiffness and how those will affect our roll, and if we're controlling our vehicle the way we want in roll. So if we look at the static case, I'm drawing kind of, you can of course picture a different roll center for your actual suspension, but I'm just drawing this swing axle suspension, and I'm drawing a spring that's so that the spring would exactly match the wheel rate. But imagine this KW is your wheel rate, and this roll moment, HRM, is the height from your roll center to your CG. And then you have your track width, TW. So in the case of a roll, let's say it's making a left-hand turn, it's rolling to the right. You have this fictitious force, sprung mass times lateral acceleration here. And then that'll cause this to roll by an angle phi. And so the distance that you travel up and down on relative to your wheel is going to be equal to phi times your track width over 2. That's just angle times radius. And so the force that's going to produce here is going to be just the wheel rate times that change in displacement vertically. And if you want to get the moment, so in this case, we're talking about roll. So we're going to look a lot about roll moments, about the roll center. So the moment about the roll center is we're going to have both sides, and we're going to have this force times a track width over 2. So that's why you'll get a force, a distance. They both have track widths over 2 in them, and you're going to, if you normalize this by the amount of roll that you get, that'll be your roll stiffness. So this roll stiffness, you'll see it's related to your wheel rate, and typically you'll look at this for the front and the rear separately, because you'll have different wheel rates in the front than you will in the rear. And you could potentially also have different track widths as well. So those will be your roll stiffnesses. And then what we might want to actually care about is how much total are we going to roll, or how much do we roll per lateral acceleration? So in this case, we have to know, for a certain amount of moment about the roll center, how much will we roll? But we also need to know, okay, well, how much moment is there in roll? So the moment in roll will be this mass times lateral acceleration. This should be sprung mass times this height of the roll moment, divided by our roll stiffness. And sometimes because this CG comes out from under the roll center, you'll see a term that will come in the denominator as a result of that. And so we had our roll stiffness. This is the roll angle. So you might want to make sure that you're not running out of tire travel with this roll angle, which you can multiply the roll angle by the track width over 2 to get how much your tire is moving. And this will give you what's known as the roll rate or roll flexibility. So it's how much you're going to roll per lateral acceleration. And you'll see how we use that going forward. So, and these two terms are your roll stiffnesses of your rear and front, which could include anti-roll bars. To talk about using anti-roll bars, first what we need to talk a little bit is about your lateral load transfer distribution. So also LLTD, or total lateral load transfer distribution, is what some people call it. So if we look at a top view of the vehicle and you're accelerating, let's say you're accelerating, making a right-hand turn, you're going to have weight shift out to the left-hand wheels from your right-hand wheels. And keep in mind that the weight shift happens from front wheel to front wheel and from rear wheel to rear wheel. You don't have cross weight transfer. It's not like the CG is moving forward and back. And the total of that is this, what we've talked about before, mass times acceleration times height of the CG over the track width. And you want to be able to control how much of this is happening in the front versus the rear. So, because as we've talked about before, the more weight transfer you have, the less grip you have. So if you have more weight transfer on the front axle than you do in the rear, you're going to lose more grip on the front relative to the rear. And what that's going to cause you to do is understeer, for example, or do the opposite case or vice versa. And so this weight transfer, this weight transfer on the front and the rear, happens both just through your suspension links. So these are the weight times the height of the roll centers. But they also happen through your suspension. So these terms are what goes through the suspension. And so you have your roll stiffnesses and your roll rates. And what you're going to want to make sure is that this lateral load transfer distribution is matching is like that common kind of roughly common ratio of your weight distribution, as well as your grip and your aerodynamic down forces. Typically, what your vehicle, because of these compliances in the system and things that we're neglecting, will cause your system to understeer. You'll typically make this slightly more in the oversteer category, where you'll actually have slightly more weight shift in the rear than you would for kind of this perfect ratio. And what you might find is just looking after doing your ride frequencies for your front and rear, you might not have the right lateral load transfer distribution. So you might add an anti-roll bar, which only adds, it's a nice way to only add stiffness in roll, but not in heave motion. So when a tire travels up and down. So one way to do that is by adding some roll stiffness from an anti-roll bar. So in this way, the roll stiffness is always related to the wheel rate. You can also relate this to the portions of a bar that goes across, and we'll usually have a small moment arm on it that will be attached to some of your suspension links. And so this is roughly, I just put in some values for the shear modulus, for the torsion constant, your track width, the motion ratio of your anti-roll bar, which is how much your wheel travels relative to how much the end of your anti-roll bar travels. The radius is the distance from the end of your anti-roll bar perpendicular to the axis at which you're torsioning your anti-roll bar, and the length of your anti-roll bar. I actually did find a great derivation on this, so we actually worked on this with a few students recently. So if you've seen a nice paper on finding this for your typical anti-roll bars, that would be cool. So that's a little bit about getting your lateral load transfer distribution and getting the balance of your vehicle right. And so in the end, you'll want to make sure and go back to that you're not having too much travel, that you're bottoming out your suspensions. So there's plenty of things I haven't discussed here, which are some things to remember, is that you have this motion in roll, which we talked about, and we talked about some heave motion, but you also have pitch and single tire upsets or twist, also known as warp, that you will want to take into account. Might check into those frequencies and what's the max travels, and is that acceptable? And keep in mind, you even see a few of the top teams these days, even including a third element spring, a heave spring to control just the heave motion. And so you can look a lot into how you can achieve that, but that's a nice way where not only can you control the motion of one wheel up and down as well as roll, but you can also control heave, especially for vehicles with larger aero packages. I haven't talked a lot about the damping, but you want to optimize your damping to reduce the load variation at the contact patch. And so that's one other thing to keep in mind. Things don't always have to be linear here, right? And so your dampers, you might have your dampers and springs might have a rate at low speeds and displacements and a different ones at high speeds and high displacements, especially when you're getting near the end of travel. You might also have motion ratios that increase with travel to increase your wheel rate as it travels. You also want to keep in mind with your suspension that you're talking with your chassis members and making sure you have a stiff load path for these suspension members. You want to be feeding them into nodes where possible, and over distances inside the chassis. And if your chassis is very compliant, so you might not have good torsional rigidity, for example, then your analysis is only going to be as good as the compliances in their system. And so unless you're taking that into account, you're going to want that to be much stiffer than your system is. That also includes things like your rods to control the toe to be, have large moment arms and to be at right angles, so that you reduce the forces in those and the amount that they displace. Because keeping in mind that everything is a spring, and so there's compliance in the system that you might not be including, and there might be even compliances in the joints. And so once you get very stiff members, you'll find that the compliance in your joints might be dominant. So you also want to make sure that your system has some adjustability. You're not going to be able to build it exactly at the right camber angle and the right toe. So you probably want some adjustability for things like camber and toe. And that's also because as we've said many times, you can't stress how important it is to test and to tune and to make modifications and to iterate, to really dial in all of these parameters that we've talked about on your suspension, and make sure they're meshing with with your driver's abilities. So, and I'm sure I forgot something myself here, but I hope you found this video useful. Check out some of our other videos or some of our workshops where we do go into some of the derivations and some example problems. And so thanks for your time, and good luck out there.
Stars, I'm a fool for your love.